Today we are going to discuss about Hooke's law. Starting to lecture number 3, lecture number 4. Lecture number 4 topic was section 1 related to forces and motion, and for subtopic we will have to move towards Hooke's law. Hooke's law states that within the elastic limit, if I go for the basic properties of a substance, there is an elastic property and there is plastic property of a substance. There is also, we can say, yield limit, and there is yield limit, and there is ultimate tensile strength over there. These are some characteristics in which brittle and ductile substances are playing their roles over there. Brittle and ductile substances. For example, I take rubber band, ductile substances. For example, I take a rubber band over there. What happened? That, for example, there is a rubber band. This is a rubber band. I want to pull it up. What will happen? It will be elongated up to final limit where it will break. That is called ultimate tensile strength of it. And after crossing its elastic limit, it is going to be broken down. It happens with the brittle substances. If I go with ductile substances over there, then what will happen? That ductile substances will, for example, I'm taking a spring. What will happen? It will be, if I pull it, what will happen? It will be pulled in this form. And if I cross the elastic limit, it will not come to its original shape over there. It will not come over there, but it will not break. That is called the yield limit. And ultimate tensile strength is the limit until it break over there. And the property within which the substance is returning back to its original shape, that is called elastic limit. And plastic limit, when it is deformed, like in the form of spring over there, but it is not broken down, is called plastic limit. And yield limit and ultimate tensile strength, brittle substances and ductile substances, with their examples I have explained here. Brittle, I said, related to brittle band. Rubber band over there. Ductile, I said, a spring made up of some material like iron or copper wire over there can be taken into account over there. So Hooke's law, if we, for example, I am taking a spring or I am taking any wire of some length, what will happen? I am exerting a force of, I am making some end is fixed over there, and on this direction, I am exerting a force over there. What will happen? It will be elongated in this direction, and it is extended a little bit, and there is its change in length over there to be shown over there in the form of this. That is called change in length. So we can say, if I say its original length is L naught, and now the change in length is shown over there, then I'd say if a metal wire is supported from some weight or some, if it is supported vertically downward with the help of some weight over there, then it stretches and the weights pulls down the force F, producing an equal and opposite force at the support. If I'm not getting in the form of horizontal, I'm taking in the form of vertical form, and this string and the mass is being attached and that is being loaded over here. What will happen? It will exert force, and original length, that was this one, when no weight is added, then delta L, change in length, is going to be introduced when weight is added over there. So this is called extension. This is called we can say simply strand, stress and strand. Strand is change in length over original length over there. Send for this one, Robert Hooke in 1676 gave a law, 1676, 78, sorry, 1676. Okay, that the extension of a stretched wire is directly proportional to the load or force over there, where we can say change in length is directly proportional to load or weight or force over there which is applied for its extension over there. So here the relationship was called Hooke's law, like a metal spring obeys Hooke's law. If a pair of opposite forces are applied to at each end over there, we can observe over there. Now, if I draw a graph between the Hooke's law for different purposes over there, then I will say here that Hooke's law is going to be defined as with the help of a graph over there. If I say here, this is a graph between some extension on this side and force on vertical side, then I am saying the graph will stay straight line. And after some limit, it is going to be taken as a bending over there. Then we can say here that Hooke's law being obeyed when until the graph is straight line. And after the curve, Hooke's law is not obeyed, in which force and extension is directly proportional over there in the form of change in length or force or weight over there to be provided by getting the relationship over there. So there is the limit of force you can apply Hooke's law to stay true. The graph shows force against extension for a typical metal wire. So the first part of graph obey and straight line relationship between force and extension can be shown from here to here. This is being shown by a straight line curve over there. So this straight line curve is showing the relationship where both are directly proportional to each other.
कहते हैं आपसे बात करने मैंने कहा कहते हैं आपकी तबीयत कैसे होती
And force and extension over there. There is a limit you can apply. So first part of this graph is showing the elastic limit over there. After that, there is a plastic limit where it is getting deformed. And this is the ultimate tensile strength, UTS point. This is yield limit, where it is not broken down over there, yield limit. So after this limit point of brittle substance is going to broken down is called brittle substance, and when it is getting deformed, that is called ductile substance over there. So remember that whenever the Hooke's law is going to be discussed over there, there should be straight line which is following the Hooke's law is the form of straight line relationship over there. When the force becomes greater enough, the graph starts to curve over there, and the point where I am marking here as E point is called elastic limit over there. And if you increase the force past the elastic limit, then the material will be permanently stretched. And when all the force is removed, will not the substance will not be longer than at the start over there. It will be deformed in completely shape over there. So until a material can return to its original shape after the elastic deformation, then it is called elastic behavior. And metals display this elastic behavior as long as Hooke's law is obeyed. So mostly metals in the form of spring obey this behavior over there. So always keep in mind, here is no formula is required or like that for calculation. Only you will have to go for explanation, understanding over there. And this can also be done in the form of experiment, which can investigate Hooke's law with a spring in the form of practical. So Hooke's law stops working when the force is great enough. Remember that it will show some curve over there. So always remember that Hooke's law will hold until we can say will hold until elastic limit is working. Elastic limit is working. After that, if I go towards some complicated concepts behind it, we will go in our A levels like that. And there we will also take the formula F is equal to Kx, and we will use for force and extension relationship. For energy, we will use 1 by 2 Fx area under graph over there. And this is will be given spring constant in the form of K, and we will go for gradient. For area under graph between F and X, we will go for energy. That will be elastic potential energy. Then we take area under graph. So these discussions will be area under graph. These discussions will be taken only in the form of, we can say, when we are going to discuss about the numerical sections of A levels over there. And also there will be Young's modulus, that will be like stress and strain is directly proportional to each other. That will also be discussed in A levels over there. But right now, you will have to go only for that extension is directly proportional to the force or weight applied on any object for its stretching purposes. After that, I am moving towards stopping distance over there. Like stopping distance is basically depend upon that what is the condition of the tires of a car, what is the your speed to stop that. You will have two types of distances there: thinking distance and stopping distance over there. So for that purpose, if I go for stopping distance to be discussed over there, then I will say here that we should go properly towards stopping distances. Distances over there. So these stopping distances is basically how simply they look for. If you need to stop a given distance, then the faster you are going, the bigger braking force you will need. But in real life, there are loads of other factors too. Many factors affect your total stopping distance. And the stopping distance of a car is the distance covered by the time between the driver first spotting a hazard and the car coming to the complete stop. So there is a pretty keen on this for exam question. So make sure you learn it properly over there. And the distance it takes to stop a car is divided into the thinking distance and braking distance. So this is divided into two main parts over there. Braking stopping distance is divided into thinking distance, and the second one, which I mostly named that braking distance. So your stopping distance is equal to thinking distance plus braking distance over there. Whenever we are discussing about stopping distance over there, then thinking distance is the distance the car travels in the time, like thinking distance I'm talking now. Thinking distance is basically the distance the car travels in the time between the driver noticing the hazard and applying the brake. Noticing the hazard and applying brakes. That is called your thinking distance. And remaining, I will also say there will be two main factors which will affect it directly. It's two factors for thinking distance over there, which I will say here. It will how far it will depend upon how fast you are going. It will also affect by your reaction time. So both of these factors are depending upon, like obviously, if whatever your reaction time, the faster you are going, the further you will go like that. You will travel more. And this is like if you are going towards your reaction time, this is affected by the things like tiredness, drugs, alcohol, and old age like that. Inexperience can also affect your reaction time over there. After that, braking distance. Braking distance, now yeah, the condition of road, the condition of tires. Like first one is the same as like in thinking distance, like how fast you are means how fast you are uh, going is the first factor. After that, the second point, which is most important, mass of the vehicle. Like you are driving the truck, or you are driving a bicycle, or you are driving something else that can affect your braking distance over there. How good your brakes are, the condition of brakes. Condition of brakes over there. At number four, I will say that how good the grip is, like road surface, weather, tires, like how good the grip is. How good the grip of tires and something else, how good the grip is over there. So in all of these cases, I will say thinking distance and braking distance will be participating to take part into the main section over there. So to avoid an accident, I will also say how good grip is. So I will add their factors also here. I will say here road surface means you are going on a slippery road or you are going on a rough surface over there, sandy road over there, or you are going towards weather condition. Is there rain water or over there, or it is dry weather condition over there. At number three, I will say the condition of the tires. If it is new, then the brakes are good. If they are old, then they are much more eroded and they are not going to stop easily. So I will say add to here that to avoid an accident, drivers need to have leave enough space between their car and the one in front so that if they stop suddenly, they can do it so safely. Enough space means stopping distance for whatever the speed they are going at. Speed limits are important because speed affects the stopping distance so much. So always remember that speed affects a lot, and keep a safe distance, keep a safe stopping distance over there. So that you can have enough time, enough distance to according to your speed limit where you are going over there can affect you to drive safely and go safely over there. After that, I am going towards moments and a little bit collisions over there. I have discussed in some previous classes also about the momentum, but today we are going towards momentum first. Okay, momentum is basically quantity of motion of an object. Quantity of momentum. Momentum is quantity of motion of an object is called, we can say, of an object is called momentum. It is a vector quantity. It is being taken in the form of unit kilogram meter per second, or its unit is Newton second over there. So I will say here that when we go towards its formula, and then we say that momentum P is equal to mass multiply velocity. If mass is high, momentum is high. If velocity is high, momentum is high. If both are high, momentum is definitely high over there. So always keep it in your mind that momentum is a vector quantity and has size and direction over there. Size, or we can say magnitude, plus direction over there. So forces mostly causes change in momentum over there. So if I go for force over there to take that phenomenon, when a force acts on an object, it causes change in momentum. Like force is equal to change in momentum over time taken over there. So always keep in your mind that it will also be written as F is equal to uh, mv final momentum minus mu as initial momentum over time taken. And from here, if I make change in momentum as a subject over there, then I say force multiplied time is equal to mv minus mu. So both cases should be taken over there. So from here, I can get the change in momentum or momentum unit as Newton second, which I have written it for you. So whenever, for example, I give you the example over there that how the momentum before and after should be taken to find the force over there. You can take the example of a gun. When it is firing, a gun fires a bullet, and at which speed it is going to come back, and showing the positive and the negative to the right and left, because in the initial momentum, if they are equal, and both can be taken in the form of this formula. So this formula, keep it in mind, and we will mostly have this question in our papers over there in paper 1 according to IGCSE Edexcel over there. So a larger force means faster change in momentum, and so greatest acceleration over there. I will say from here, if I want to use this relation, I will say if there is a larger value of force, then I can also say force is equal to mass into V minus U over T. This internal one is equal to acceleration over there. If I say here that change in momentum is at faster rate, means the time is smaller, the force will be larger, and force will be larger, then definitely acceleration will be larger over there. Likewise, if someone's momentum change very quickly, like a car crash or like that, then the forces on the body will be very large and more likely to cause injury to the driver over there. After that, I will say here that this is why cars are designed to slow people down over a longer time when they crash, and the longer it takes for a change in momentum, the smaller the force and injuries to be likely like that. So, crumple zones on impact, increasing the time for a car to stop over there, and seat belts stretch slightly, increasing the time taken for the wheeler to stop. And this reduces the forces acting on the chest over there, so the driver is safe a little bit. Airbags also slow down more gradually over there. So we can say here, all these cases are basically to decrease the momentum effect in the form of force over there. After that, I am moving towards turning effect of forces. So turning effect of forces means we can say here turning effect of force, that is called moment also. Turning effect of forces and center of gravity. Turning effect of forces. Effect of forces is called moment, or we can also name it as torque. It is vector quantity, having the unit Newton meter over there. And we can also say, as it is a vector quantity, it has magnitude and direction also, size or direction also. So we can take both them into account for making the turning effect of forces over there. And if I go for its formula, then I will say here that moment is equal to force, which is applied at one end, multiply perpendicular distance between line of action and pivot. perpendicular distance between line of action of force and pivot. So I am saying here, for example, you are taking a wrench over there to untie this nut over there. You are applying the force over here. This is your line of action of force. And this is your axis along which the body is rotating over there. And you are applying the force, then the perpendicular distance here is showing your perpendicular distance between, this is pivot, this is line of action of force, that is called moment arm. So to show this relation over there, I will say that force on this spanner causes the turning effect or moment on the nut over there. So larger the force mean larger the moment over there. So using longer spanner, the same force can exert a larger moment. And because the distance from the pivot is greater over there, so to get the maximum moment of the turning effect, you need to push the right angles to the spanner over there, and pushing at any other angle means smaller moment because the perpendicular distance between the line of action is smaller over there. So always keep in mind when you are going towards the moment to calculate over there, you will have to keep the force perpendicularly acting at some distance, and you will have to get that distance to be multiplied with force to get the moment over there. After that, if I go towards center of gravity basically is the point on a body, the point on a body where whole weight of a body, whole weight of body appears to act downward, appears to act downward under the action of gravity. This is called center of gravity over there. And I will simply say here, if, for example, you are taking some object to hang vertically downward through a patch or pivot over there, what will happen? It will act to appear downward. And for example, you are getting some weight to be suspended through string, through a fixed support over there. It will be start hanging downward with a freely body. And if I say here that the body which I am getting its pivot, then I'm saying here, for example, I'm getting a square. What will happen if I join its chords over there like this, diagonals over there, then I'm getting its center of gravity at the center. On the other end, if I go for a rectangle over there, again, I will join their diagonals. And by getting this intersecting point, I will say it is the center point. If I go towards circle, triangle, everything, I can get the center point over there. But if the shape is not regular, then what will happen? I will have to hang, for example, I'm saying I'm getting this shape of body. First, I will hang it through this patch. What is happening? It is hanging vertically like this. And then I am getting another patch which is hanging like this. Then I am getting another patch to hang like this. It is hanging like this. So this is the center of gravity which I will obtain in this form, where its weight is appearing to act downward. Then for irregular object, I will get this phenomenon for this. So the last section related to moments is to talk about principle of moments. Principle of moment. For example, you visit a park with your friend over there, and there is seesaw which is supported on a pivot over there. If your friend is too much fat, like having the mass of 100 kg like that, then you will place your big friend at a far distance, at a closer distance, and you will sit. If you are lesser in weight, then you will sit at very far distance over there. Why I am saying so? I'm saying so because uh, then this object should come. Wait a second, I'm getting here the complete concept behind it. I'm getting to remove this. I'm saying here you will have to put your friend near the pivot who is fat, and you want to balance their weight. Then the distance from its pivot point to the distance from to the friend which was fat. On the other end, the distance between the center pivot here, like this, and like this over here. And this is distance 2, this is distance 1 from the pivot over there. This is mass 1, this is mass 2. So according to its weight, it is having a F1 acting in clockwise direction, and it is F2 and D2. There is anti-clockwise moment present over there. So when the bodies are in equilibrium, when the body are in equilibrium, the sum of clockwise and anti-clockwise moments are equal, and the objects are in we can say equilibrium over there. So for this one, we use this formula: F1 multiply D1 is equal to F2 multiply D2 over there. So by observing this free body roughly diagram over there, they are going to get support. Remember that here F1 and F2 is not equal. They can be varied according to their distances to get the balance over there. So if the total anti-clockwise and clockwise movements are equal, then the resultant moment will be equal to 0. And then we can say, if I'm just subtracting it on other side, then we are getting sum equal to 0. So summation of moments at equilibrium will have their value equal to 0. So always keep in this formula in your mind we will use for getting the support over there. So this was your section 1, which is completed in the form of forces and motion. And in the next class, we will start the section 2, and we will be focused according to the syllabus, which is required according to exam. No extra in explanation will be provided. So kindly stay connected with my channel, and thank you so much for today. Allah Hafiz. Kindly subscribe my channel and like the video. Thank you so much. Allah Hafiz.